So this is part 4 for the Spring 2023 College Algebra Exam 3 review, and we're looking at question number 32. Solve the following logarithmic equations, give an exact solution and approximation to 4 decimal places as needed, and show all work. And for letter A, we are given log base 3 of 2x plus 5 equal to log base 3 of 5x minus 13. Okay, so since I know that both sides of the equation are log base 3, essentially I just need these two expressions to be equal to one another, right? I want 2x plus 5 to be equal to 5x minus 13. Okay, and then I'm just solving for x. So I'm going to add 13 to both sides and subtract 2x over to combine my like terms. So I get 18 is equal to 3x, and then I just divide by 3 on both sides, and I get x is equal to 6, right? Another way that I thought about this problem is essentially I want to get rid of the log base 3 part of each expression. So I'm writing this as 3 log base 3 of 2x plus 5, which is equal to, and if I do something to one side, I got to do it to the other. So 3 log base 3 of 5x minus 13, right? And we know that 3 and log base 3 of x are inverses, so I'm just left with 2x plus 5 equal to 5x minus 13. Perfect. Okay, so let's look at part B. Part B says log base 6 of 7x minus 2 equal to 1 plus log base 6 of x plus 5. Okay, so on this one, it might be helpful to move all of our log base 6s on one side and everything else, leave it on the other side, right? So I can rewrite this as log base 6 of 7x minus 2 minus log base 6 of x plus 5, and this is equal to 1. And then I know using my logarithmic rules that if I'm subtracting two logs, it's the same thing as keeping the same log with the same base and dividing whatever is inside. And this is still equal to 1. Okay, I know that log base A of B, if it's equal to C, I can rewrite this as A to the C power equal to B. Okay, so I have 6 raised to the first power is equal to whatever is in the inside might be 7x minus 2 over x plus 5. Okay, so continuing on, I can multiply both sides by x plus 5, and on these on our right hand side it goes away, right? So I'm left with 6 to the first power is just 6, so I'm left with 6x plus 5, which is equal to 7x minus 2. And then I get 6x plus 30 is equal to 7x minus 2. Okay, and then just a little bit more simplification, I get that I'm going to combine my like terms, right? So I'm going to move the 6x over. So I get 30 is equal to x minus 2. And then I'll move the 2 over. So I get 32 is equal to x. Okay, and so for the last part, I have that log part C, I have that log base 2 of x is equal to 4 minus log base 2 of x minus 6. Likewise, I want to combine all of my logs on one side and anything else without the log on the other. So I can say that this is the same thing as log base 2 of x plus log base 2 of x minus 6, which is equal to 4. Okay, and then using my logarithmic properties, I know that if I'm adding two logs, I can keep the log and add whatever and multiply whatever is in the inside. So log base 2 of x times x minus 6, which is equal to 4. Okay, and then I know that I can rewrite this in terms of exponentiation, right? So I have 2 to the 4th power is equal to x times x minus 6. Okay, 2 to the 4th power is 16. And then I get that this is equal to x squared minus 6x. Okay, and so I'm going to move over that 16 so I can set this equal to 0 and solve for x, right? Okay, so I need two numbers such that when I multiply them together, I get 16, and when I add them together, I get negative 6. Okay, so I see that I can write this as x minus 8 and x plus 2. Okay, so therefore using my zero product property, x is equal to positive 8 and x is equal to negative 2. Okay, and the last thing that I have to realize is that if I plug in x equals negative 2 back into my original expression or equation right here at the very tippy top, right, I see I cannot take log base 2 of a negative number. So this does not work. My only solution is x equals 8 because x equals negative 2 is an extraneous solution. Okay, cool. Question number 33, solve for the indicated variable. So A says A is equal to P times 1 plus R over N raised to the N times T power, and we want to solve for T. So the first thing I want to do is get rid of that pesky P, so I'm going to divide both sides by P. So I get A divided by P is equal to 1 plus R divided by N raised to the N times T power. And now I'm going to take a natural log of both sides. So the natural log of A divided by P is equal to the natural log of 1 plus R divided by N raised to the NT power. Okay, so now that I know that if I have something in a log raised to a power, I can bring down that power in front of the log, right? So I can rewrite this as the natural log of A divided by P equal to N times T times the natural log of 1 plus R divided by N. Okay, and now since I just want to solve for T, I can divide this side by N times the natural log of 1 plus R to the nth power, right? As long as I do it to the other side. Okay, so on this side, we see some things vanishing, and I am left with the natural log of A divided by P divided by N times the natural log of 1 plus R divided by N is equal to T. Okay, so for part B, we have log B minus 1.7 equal to 2.3m. And I want to solve for b. So I want to move everything to one side that's not associated with the b. So I get log b is equal to 2.3m plus 1.7. And then since there is not a number in this base, I can assume that it is a 10, right? So I want to raise everything to the 10th. I want to take everything and put it in the exponent and have the base be 10. So I can write this as 10 raised to the log base b of 10 of b, because there is a hidden 10 right here, is equal to 10 raised to the 2.3m plus 1.7. Okay, I know that 10 raised to the log base 10 of b is just b, and this is equal to 10 raised to the 2.3m plus 1.7 power, and that is my final answer. So for 34, Matilda and Horace open a retirement account with $120,000. How many years will it take for the money to grow to $800,000 if it grows at a rate of 4.5% compounded monthly? Round to the nearest year and show all work. Okay, so I know that our formula we are going to utilize is A equals P times 1 plus R divided by N raised to the N times T power, right? A is our final amount, P is our initial amount, R is our rate, N is the number of times we are compounding it per year, and T is our time. Okay, so we're looking for years, right? So we're looking for T. Okay, so I can plug and chug everything that I know. So 800,000 is my final. They're starting with 120,000. Oops. Let me get the eraser. Is equal to 120,000 times 1 plus my rate, 0.045 divided by 12 raised to the 12 times t. Okay, so I'm going to divide over this 120,000. Then I can see a bunch of things, a bunch of these zeros start going away, right? So 80 divided by 12 is the same thing as 20 divided by 3 equal to 1 plus 0.045 divided by 12 raised to the 12t power. Okay, so now I gotta take a natural log of both sides. Plus 0.045 divided by 12 raised to the 12t power. I know that since this is a log with an exponent inside, I can bring down this exponent using my rules. Okay, and then since I'm solving for t, I can just divide by everything else. So I'm going to divide by 12 times the natural log of 1 plus 0.045 divided by 12 on both sides. And on this side, those go away, and I'm just left with t is equal to the natural log of 20 divided by 3 divided by 12 times the natural log of 1 plus 0.045 divided by 12. And we get that this is approximately 42 years, because we want to round to the nearest year.
Okay, for this next problem, we're going to look at number 35. So it says the population of a rural community was 3,050 in 2010. The population had increased to 3,500 in 2015. Assuming exponential growth, find the following. So before I even get to that, I want to write down our equation for exponential growth. So our population as a function of time equals our initial population, or P naught, times e to the RT. Okay? And so it says, first we need to find the growth rate to 4 decimals and as a percentage. So our P naught from the problem is 3,050. And let's define T as years since 2010, since 3,050 is our initial value. And so we know that the population is 3,500. This is equal to 3,050 times e to the r times 5, right? Because that is the population 5 years after 2010. So next what we're going to do is we're going to divide both sides by 3,050. And this is equal to e to the 5r. Let me see what that is. 3,500 divided by 3,050. I'm just going to leave it like that. So next we're going to take the natural log of both sides. So natural log of 3,500 over 3,050 equals 5r. So r equals 1/5 times natural log of 3,500 over 3,050. And this is approximately, let's see, natural log of 3,500 divided by 3,050. This divided by 5. So this is 0.0275. And as a percentage, that is 2.75%. So that is part A. Okay, so next we want to estimate the population in 2022 if this trend continues. So what it means by if this trend continues is that R is going to be the same, our rate is going to be the same. So if our time is 2022, this is going to be 12 years after 2010. So this is going to be P of 12. This will equal 3,050 times e to the 0.0275 times 12. And plugging this into the calculator, we will get, let's see, this is equal to 4,243. So I'm going to round up because we can't have 0.4 of a person. So 4243, or maybe 4242 if you need to round down instead. So that is our estimate of the population. Okay, next, problem 36. So a sample found at a dig site was determined to have 68.78% of the C14 still remaining. Use the model Q of T equals Q naught times e to the negative 0.000121 times t to determine the age of the sample round to the nearest year. Okay, so Q of T, I'm just going to write down our model here. So if we know that we have this initial amount of C14, Q naught, and there's 68.78 of it remaining at a certain time, we can say that Q of t is 0.6878 times Q naught. So this is equal to Q naught e to the negative 0.000121t. So now I'm going to divide both sides by Q naught. So 0.6878 equals e to the negative 0.000121t. Now I'll take natural log of both sides. So natural log of 0.6878 equals negative 0.000121t. And now I'll divide both sides by that decimal. And so I will get that t is approximately, so natural log of 0.6878 divided by negative 0.000121. And this will be 3,093 years. Okay, next we're looking at number 37. It says the population of California, P of t, which is in millions, can be approximated by the logistic growth function P of t equals 95.2 divided by 1 plus 1.8 times e to the negative 0.018t, where t is the number of years since the year 2000. So for part A, we want to determine the population of California in the year 2000. So this is basically just P of 0, since t is the number of years since 2000. So we're just going to take our function and we're going to plug in 0 for t. So plus 1.8 times e to the negative 0.018 times 0. And if I plug this into my calculator, I will get 95.2 over 1 plus 1.8 times e to the 0, which is just going to be 1. And this will be 34. So this is 34 million. And it says round, but it's an exact number here. So the second part, we need to determine the population of California in the year 2022. So now we're going to do P of 22. So this will follow a similar process. I'm just going to go ahead and plug this in. So 95.2 over 1 plus 1.8 times e to the negative 0.018 times 22. And this is approximately 43.0. So that's 43 million. Okay. Next, we want to use the model to determine the year when the population of California will reach 68 million, rounding to the nearest year. So now, instead of being given a t value and solving for the population, we're given a population value and we're going to solve for the time. So we know that our population is equal to 68 million. And so this will be 95.2 over 1 plus 1.8 e to the negative 0.018 t, like this. Okay, so first I'm going to multiply over the fraction. So 68 times 1 plus 1.8 e to the negative 0.018 t equals 95.2. And then I'm going to, let's see, I want to divide over the 68. So 1 plus 1.8 e to the negative -0.018t equals 95.2 over 68. Subtract 1 from both sides. E to the -0.018t. There's just a lot of algebra in this problem, but it shouldn't be too hard as long as you pay attention to it. Okay, and then I'm going to divide both sides by 1.8. So we are here. Okay, then just like before, I'm going to take the natural log of both sides. So -0.018t equals natural log of 95.2 over 68 minus 1 over 1.8. And so then to solve for t, I'm going to take this natural log, whatever that result is, I'm going to divide it by -0.018. So t is approximately, just give me a second to plug this in. So we will get that t is approximately 84. So this means that the population of California will reach 68 million in the year 2084, since t is the number of years since 2000. Okay? Okay, so the last part we need to look at is the limiting value of the population of California under this model. So you can find this out using graph, using a table. There's a number of methods. But what happens is that the limiting value of the population of California will actually just be the numerator in that fraction that we have in the model. So the limiting value of the population is just going to be 95.2 million. But I encourage you to look at a graph, look at a table to see how when the x values get very, very large, or the t values get very, very large, that the population approaches 95.2 and actually stops there.
So for question 38, it says the table gives the diameter in millimeters of a sugar maple tree, along with the corresponding age in years for 6 different trees. And then it gets the table. Part A, state which model best represents the data using the graphing capabilities on my calculator. So what I did was I went to stat, edit, and I entered in all my x values in L1, and I put all my y values in L2. And then what I did was I went to second stat plot, and I went to plot 1, and I turned it on. And that will, if you see under X list and Y list, it has L1 as the X list and L2 as the Y list. And if you turn it on, it's going to plot all the points. Then what I did was I went to the window, and I changed my window from 0 to 500, because that's how big the X values are. And then for the Y value, I just went from 0 to 100, because they all fit inside that range. And then I can finally go to the graph and I can look at my points. And I can see on the graph that my points look something like this. So we have one like all the way down here in this corner, and then they go like that. And so if we kind of connect those dots to look like that, that's going to be a log graph, right? So we know we're going to be dealing with a log function. So then it says use the regression capabilities of your calculator to find the regression model from part A that best fits the data around the 2 places. All right, so now we're going to go into stat, calc, and go all the way down to ln reg. we click that, it should give us we should get what our L and reg, and we should get our y equals a plus b ln of x, which is what we're looking for here. And we get that a is equal to 3.333, or just 3.33, because we're rounding to 2 decimal places, so that means b is going to be equal to 14.93. And our r squared value is equal to 0.999, so we know it's a pretty good, accurate model. Right, so that means that our equation is going to be y equals 3.33 plus 14.9 ln of x. And now we're going to use the model from B to determine the age of the maple tree when it has a diameter of 150 millimeters rounded in the next year. Right, so we look back at our table. X is in millimeters, Y is in years. So that just means we have to plug in 150 into X, and that will give us our answer, round to the nearest year. So 33.33 plus 14.93 ln of 150, and that gives me a y of 78 years. Right, and that 78 years is in between 100 and 200, right? That's in between 72 and 82, so we're pretty accurate with that answer. So this is the end of part 4 of your review, and this is the last review. So if you made it this far, good luck on your test, and we'll hope to see you again.